Dear Chairman, ladies and gentlemen, skin diseases and dermatology problems depend on many factors. One of the reasons is the damage of stratum corneum by the various substances. I'd like to present a part of study which I did with my team. The title is Consequences of Overcoming a Human Skin Barrier by Low Molecular, Cyclic and Linear Methyl Siloxanes silicones. What are the silicones? Polysiloxanes are commonly named silicones. They belong to the organosilicon chemical compounds. Polysiloxanes are composed of backbone with repeating silicon and oxygen atoms and various chemical groups, for example, methyl, ethyl, propyl, phenyl, vinyl. Depending on the size of molecule and the shape of skeleton, polysiloxanes can be linear, cyclic, branched, cross-linked first networks, and cross-linked second networks. In case of linear, these are volatile and non-volatile fluids, for example, dimethicone, cyclic, for example, cyclomethicone, branched, for example, silicone rubbers, soft skin adhesive from Dow Corning Company, cross-linked first networks present in resins, rubbers, and elastomers. Elastomers is a very important group because are used to treatment keloids or scars, for example, Sika care. An important group of silicones are linear polydimethyl siloxanes and cyclic polydimethyl siloxanes. They have methyl group and a various degree of polymerization. Therefore, linear polydimethyl siloxanes can be low molecular weight, medium, and high molecular weight. I'd like to note that according to the pharmacopoeia, only medium molecular weight can be used orally. In medicinal products, simethicone and dimethicone are used as anti-foaming drugs. The researchers argued that the medium molecular weight is safe for human being. Currently, I am interested in research with low molecular weight, both linear and cyclic. On the following slides, I am presenting a few examples. Why should we be interested in silicones? It's estimated that the sale on the global market for silicone will be until 2017 more than $19 billion, and report about silicones presents that the global production capacity has reached 400,000 tons per year. Why should we be interested in silicone yet? Due to their unique physicochemical properties, polysiloxanes are used in a wide variety of applications. A human being has a direct contact with silicones through medicinal products as an active pharmaceutical ingredient, dimethicone or simethicone, by food as a functional additive E900, cosmetics, by medical devices, for example, implants, prostheses, and tamponade, and by environment, by water and soil, which silicones are present as contamination. Why should we be interested in silicone yet? I would like to emphasize that a human being may have a direct contact of silicones with skin through dermal medicinal products, ointments against infection pathogens, gels for keloids, ointments for scars, emollients for atopic dermatitis, and products against lice, and by personal care products and cosmetics, hand and face cream, lotions and masks, protective creams against ultraviolet radiation, face gels, antiperspirant, deodorants and shampoos, and by environment because of significant amounts of contaminant silicones found in soil, water and air. Contamination problem is described in the few reports of governments, for example, Canada, Sweden, and Denmark. Why should we be interested in silicone yet? It should be pointed out that the cosmetic industry dynamically develops in producing of personal care products and various cosmetics which contain silicones. According to the American Skin Deep database, more than 16% of the examined formulations contain polysiloxanes. By other source, the polysiloxanes are presented in every second cosmetic. Why should we be interested in silicone yet? Generally, polysiloxanes are considered as non-toxic. However, there are reports about a toxicity of polysiloxanes, both the linear and cyclic structure, and especially with low molecular weight. In literature, there is reported an impact on changing of proteins conformation, immune system, endocrine system, increase in liver enzymes, impact on the human skin, irritation and inflammations, cyst formations and genotoxicity. Regarding the safety assessment of using low molecular weight polysiloxanes, it seems to be necessary to verify the possibility to overcome skin barrier by these substances. Therefore, we ask if silicones have the ability to overcome human skin barrier. In the study, the following three issues were considered: human skin structure and its impact on the overcoming skin barrier by xenobiotics, possible pathways of entry the skin, and physicochemical properties of the xenobiotics. Human skin barrier includes stratum corneum, epidermis, and dermis, but the most important layer which determines skin barrier is stratum corneum. Stratum corneum is composed of corneocytes of hexagonal and pentagonal shape, surrounded by bilayer lipid matrix. Due to the tight stratum corneum, its effective barrier against entering undesirable allergens, compounds, and microorganisms. We can consider 6 pathways by which chemicals diffuse into the skin: through the appendages, hair follicles, sebaceous gland, and eccrine sweat gland, by transcellular permeation and intercellular lipid pathway, and through corneal desmosomes. According to the theory, Lipinski's rule of 5, through healthy skin can penetrate the low molecular compounds with molecular weight up to 500 Dalton, log pilos then 5, optimal from 1 to 3, hydrogen bond donor below 5, hydrogen bond acceptor below 10. The subject of the study were the linear hexamethyl disiloxanes, HMDS, and cyclic octamethyl cyclotetrasiloxane, OMCTS, which are ingredients of the dermal medicinal product and personal care products and cosmetics designed not only adults and children, but also infants. The aim of the study was assessment of skin barrier for HMDS, OMCTS, Determination the depth of limit permeation through different layers of the skin, stratum corneum, epidermis, dermis to fluid acceptor, and observation of interaction, silicon corneal site and silicon lipid matrix. In study, the front type diffusion cells were used and human skin was taken from corpse. Fluid acceptor, from the top of the skin, silicons as a test samples and water as a control sample were dosed. Fluid acceptor had a contact with skin from underneath, and fluid acceptor was a model of blood and lymphatic vessels. The experience lasted for 24 hours. In study, two methods were used: attenuated total reflectance, Fourier transform infrared spectroscopy, and fluorescence microscope. Spectra provided the evidence for penetration of silicon to stratum corneum. We identified characteristic bands for HMDS and OMCTS, which were located at wave number 1404, 1259, 1059. It was found that this area didn't interfere with the skin matrix. Furthermore, fractionation by tape stripping of stratum corneum layers, 4 layer, 10 layer, enabled to the assessment of the depth of penetration through stratum corneum. An important result was also a demonstration of the polysiloxane in dermis, which provided evidence of permission of silicons through deeper skin layer. To observe the microscopic image, the skin sample was stained with the following fluorescent dyes: fluorescein, sulforhodamine B, hexyl ester rhodamine B. Fluorescein and sulforhodamine B have a polar, hydrophilic, lipophobic properties and affinity to stratum corneum protein. Hexyl ester rhodamine B has nonpolar, hydrophobic, lipophilic properties, affinity to lipids. Based on comparison of control samples after application water and test sample after application HMDS, it's observed that the structure of stratum corneum is disordered. On the slide, there is visible black spaces that confirm the destruction of the stratum corneum. In the case of OMCTS, the observations were similar. Stained samples by lipophilic dye, which was hexyl ester rhodamine B, provided evidence to establish the route of entry into the stratum corneum by silicons. Lipid matrix was intensely stained in the samples after application low molecular silicons. It was evidence that HMDS and OMCTS penetrate the skin by intercellular lipid pathway. Moreover, the deformation of corneal site was observed. They lost the natural hexagonal or pentagonal shape. Three-dimensional images were the confirmation of this entry route. They also provided evidence for the existence interaction between silicon and stratum corneum lipids. Stratum lipids matrix are destroyed, we can see. Conclusions. Human skin is not a barrier for low molecular silicons. HMDS and OMCTS demonstrated ability to penetrate the stratum corneum, as well to permeate to the dermis, where blood and lymphatic vessels are located. It has been shown that HMTS and OMCTS penetrate the stratum corneum by intercellular lipid pathway. Fluorescence microscopy provides basic information about the interaction between low molecular silicones, linear and cyclic, and lipid structure of the stratum corneum. What are the consequences of overcoming the skin barrier by low molecular cyclic and linear methyl siloxane silicones? The entry to human organism of silicones can result to uncontrolled their migration. Therefore, it's necessary to carry out research. The damage of the stratum corneum as a skin barrier may cause an easier entry of microorganisms, allergens, various substances from environment. Therefore, it's necessary to carry out research. The damage of the stratum corneum can cause the skin penetration by the larger particles of substances from the medicinal and cosmetic products, which can be harmful. Therefore, it's necessary to carry out research. Thank you for attention. I'm sorry, but my English is not advanced. Therefore, if you wish to ask some question, please, after presentation, in foyer or by email. Sorry.
Thank you, Doctora. Any question for the Doctora? No?